This lecture discusses statistical inferences for two population means using paired samples. First, let's use an example to explain what paired samples mean. Consider two populations, one consisting of 5 married women and the other of their 5 husbands. Here, we also have two populations. However, each subject in one population exactly corresponds to one subject in the other population. This is why we say paired, and this is the major difference from the independent samples. Let's take a paired sample of size 3 from these two populations. It means that we choose 3 wives and 3 husbands. Because husband and wives are paired, after selecting 3 wives, the 3 husbands are uniquely selected accordingly. The table lists all paired samples of size 3. Each of the 10 possible paired samples is equally likely to be the one selected. Therefore, the chance of obtaining any particular paired sample of size 3 is 1 over 10. In this example, we want to decide whether in United States the mean age of married men differs from the mean age of married women. It is a hypothesis testing problem. The variable of interest is age. We have two populations involved in this problem, married men and married women. Let mu1 and mu2 be the mean age of married men and women. The non-hypothesis is mu1 equals mu2, and the alternative hypothesis is mu1 not equal to mu2. We choose a two-sided alternative because we have no idea which one will be larger. Because we have paired samples now, we will use a different approach to calculate the test statistic and construct confidence intervals. Notice that the observations are paired, which motivates us to calculate the difference of values directly. In the table, we can see that we have 10 couples. The table lists the age of husband and wives. For each couple, we can calculate the difference of ages. Now, if we want to know whether there is any difference for means, it is enough to know whether the difference is 0 or not. Next, we can apply the one mean t-test procedure to the difference of mean. Here, D is the difference for each pair. We can calculate the mean of difference, which is D bar. We can also calculate the standard deviation of difference, which is SD. The sample size n is the number of pairs. This t-value is exactly the t-value for one mean t-test when the data are different within pairs. Here, we need to assume D is normally distributed. The number of degrees of freedom is n-1. This slide summarizes the steps for paired t-test. It is exactly the one mean t-test applied to differences. We assume simple random paired sample. We also assume that the differences are normally distributed. If the sample size is large, the normality assumption can be weakened. To compare the two population means, we first need to choose a hypothesis correctly. The non-hypothesis is mu1 equals mu2. There are 3 different alternative hypotheses, namely two-tailed test, mu1 not equal to mu2, left-tailed test, mu1 less than mu2, and the right-tailed test, mu1 larger than mu2. We need to decide on the significance level alpha. In most applications, alpha equals 0.05. Occasionally, alpha equals 0.1 or 0.01. We can compute the test statistic as T0 equals x bar over SD divided by square root n. Here, D bar is the average of differences, and SD is the sample standard deviation of differences. We can continue with the critical value approach or p-value approach. When using the critical value approach, the choice of critical values depends on the type of alternative hypothesis. For two-tailed test, there are two critical values, plus minus T alpha over 2. The rejection region is less than negative T alpha over 2, or larger than T alpha over 2. For left-tailed test, the critical value is negative T alpha. The rejection region is less than negative T alpha. For right-tailed test, the critical value is T alpha. The rejection region is larger than T alpha. Make sure to calculate the number of degrees of freedom correctly. It is n minus 1, where n is the number of pairs. If the test statistic falls in the rejection region, reject H none. Otherwise, we do not reject H none. When using the p-value approach, we also need to calculate the number of degrees of freedom. It is n minus 1. For two-tailed test, the p-value is the sum of probabilities of less than negative absolute value of the t0 or larger than absolute value of t0. For left-tailed test, the p-value is less than t0. For right-tailed test, the p-value is larger than t0. If the p-value is less than significance level alpha, we reject H none. Otherwise, we do not reject H none. Last, make sure to interpret the results of the hypothesis test. Note that the hypothesis test is exact for normal population and is approximately correct for large samples from non-normal populations. For non-normal populations, because of the centrally limit theorem, D bar approximately follows a normal distribution. Therefore, we can still use this t-test. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean age of married men differs from the mean age of married women? We have already identified the non-alternative hypothesis before. H none is mu1 equals mu2, and the alternative is the two-tailed test mu1 not equal to mu2. The sample size is 10, which is small. We need to check the normality assumption. Notice that when checking the normality, we check normality for the difference of age, but not age of husband or wives. The normal probability plot shows that the difference of age roughly follows a normal distribution. Therefore, we can apply the paired t-test. We can calculate the sample mean and the sample standard deviation of D. The sample mean is 3.6 and the standard deviation is 4.97. Therefore, the test statistic is T0 equals D bar divided by SD over square root n. Plug in the numbers and do the math. The test statistic is 2.291. The test is two-sided with significance level 0.05. The number of degrees of freedom is n-1 equals 9. When using the critical value approach, the critical values are positive minus T alpha over 2 equals positive minus T 0.025. It is positive negative 2.262. The test statistic is negative 2.291, which is smaller than negative 2.262. It falls in the rejection region. Therefore, we reject H none. When using the p-value approach, we can calculate the p-value using Excel. It is 2 times t dot dist negative 2.291, 9, and 2. The p-value is 0.0477, which is slightly smaller than 0.05. Therefore, we reject H none. Both approaches lead to the rejection of H none. At the 5% significance level, the data provide sufficient evidence to conclude that the mean age of married men differs from the mean age of married women. We can also construct confidence intervals. It is essentially the t-confidence interval applied to the differences. The assumption includes a simple random paired sample. We also assume that the differences are normally distributed. If the sample size is large, the normality assumption can be weakened. To find the confidence interval, we first need to find T alpha over 2. Notice that the number of degrees of freedom is n-1. The endpoints of the confidence interval for mu1 minus mu2 are d bar plus minus T alpha over 2 times SD over square root n. Notice that the confidence interval has the general form of point estimate plus minus margin of error. Last, make sure to interpret the confidence interval. Note that the confidence interval is exact for normal population, for normal differences, and is approximately correct for large samples for non-normal differences. Let's obtain a 95% confidence interval for the difference between the mean ages of married men and married women. For confidence level 95%, alpha equals 0.05. Therefore, T alpha over 2 equals T 0.025 equals 2.262. Here, the number of degrees of freedom is n-1 equals 9. The 95% confidence interval for mu1 minus mu2 is d bar plus minus T alpha over 2 times SD over square root n. Plug in values and do the math. We get the endpoints are 3.6 plus minus 3.56. We can be 95% confident that the mean age of married men exceeds the mean age of married women by somewhere between 0.04 years and 7.16 years. When comparing paired T procedures with independent T procedures, what are the pros and cons? The advantage is to reduce noise, or simply, it will lead to a more accurate answer. The disadvantage is it loses degrees of freedom. In statistical inference, we always prefer larger degrees of freedom. Let's illustrate the issues in examples. For the difference of mean age of husband and wife, we have already calculated a 95% confidence interval in the previous slide. The margin of error is 3.56. If we did not recognize that it is a problem of paired samples, we can construct a 95% confidence interval for the difference of mean age by treating it as a problem of independent samples from two populations. The 95% confidence interval in this case is 3.6 plus minus 17.29. Notice that the margin of error in this case is 17.29, which is much larger than the margin of error obtained by paired samples. You can see that the paired samples lead to a smaller margin of error, which indicates a more accurate result. Why paired samples lead to a smaller margin of error? When we construct confidence intervals using the independent samples approach, there are two types of variabilities among the data: the difference within each pair, husband and wife, and the variability among couples. However, when we apply the paired sample approach, the variability among couples is cancelled out because of the calculation of difference. We only focus on the difference within each couple. This is the main reason that paired samples lead to a more accurate result. If you compare the degrees of freedom for the paired samples, degrees of freedom is n-1 equals 9. But for independent samples, the degrees of freedom is n1 plus n2 minus 2 equals 18. the degrees of freedom for paired samples is much smaller. In this sense, we say that it loses degrees of freedom. Let's use a different example to illustrate how to collect data and how to analyze data. In fact, they are connected. I mean that the approach we select to analyze data should match the way we collect data. Suppose that one company wants to compare the taste of a new recipe for cookies with an existing one. There are two different ways of collecting data. Firstly, the company recruits two groups of volunteers. One group tastes cookies from the new recipe and the other group tastes cookies from the existing recipe. Each volunteer scores the taste of cookies on a 0 to 10 scale. If we collect data in this way, we have independent samples from two populations. Each population only tastes cookies from one recipe. When analyzing data, we should use T-procedures for independent samples. There is a different way to collect data. The company recruits one group of volunteers. Each volunteer tastes cookies from the new recipe first, and then cookies from the existing recipe. Each volunteer scores the taste of cookies for both recipes on a 0 to 10 scale. If we collect data in this way, we get paired samples. The scores by the same person are paired. The first population contains the scores for the first recipe, and the second population contains the scores for the second recipe. When analyzing data, we should use T-procedures for paired samples. Here, I want to argue that the second approach is better. Firstly, we need less volunteers. Secondly, people vary a lot when giving scores. Some are generous and prefer to give high scores, and some are picky and tend to give low scores. If we use independent samples, such variability exists in your data and will mess up your analysis. If we use paired samples, such variability will be eliminated when calculating differences, which will lead to a more accurate result.